the way. Anyway, so my name is Tess Caswell, and I'm a fourth year grad student. I've taken classes with some of you guys, but I don't know some of you at all. So would you mind going around and just telling me your name and what year you are, and if you're geo or geobio, the basic info. I know who you are, but you can start, Chris.
Hello, I am Chris. I am a junior studying geophysics.
Nice. I'm Grace. I'm a sophomore studying geobio.
I'm Jasper. I'm a freshman studying something geo.
I'm Helen. I'm a freshman.
Okay.
Hey guys. I'm Elizabeth. I'm a senior and I'm studying geobio.
I'm Mike. I'm a junior studying geobio.
Grad students.
I'm Jack. I'm second year studying geology.
I'm Karen. I'm a second year studying geophysics.
I'm Tristan. I'm a sophomore studying geobio.
I'm Alan. I'm a junior studying climate science via geobio.
I'm Nick. I'm a junior studying geochem.
We were in structure together, right?
Yes.
When you were a freshman?
Yes.
Yeah. So I've taken classes with you guys. So as a fourth year grad student, I study ice primarily. Reed Cooper is my advisor. So my research kind of delves into micro scale processes that lead to macro scale deformation of ice. So those of you who have taken structure, and I think you cover it a little bit in Geo 22 as well, Jan, but mechanisms of creep, so dislocation creep, diffusion creep, how those things work together in ice to sort of affect motion on large scales. So glaciology is not my area of expertise per se, but we did have a glaciology class, and I grew up in Alaska with glaciers, like not in my backyard, but pretty much. So it's kind of near and dear to my heart. And today what I really wanted to do was give you guys kind of a sense for what you would see near a glacier and when you're perhaps on it, because I heard that you guys are hiking up to a glacier. And then to give you a bit of the background on sort of the physics of glaciers and how and why they flow. So starting with the pictures of sort of glacial geology. Jan, would you hit the light and leave on the board one, but turn off? Perfect. Okay, so as you're driving up to your glacier, you will not be seeing this exact glacier. This is one near where I grew up. This is Portage Glacier in Alaska. But there's some major features that you'll see probably on the road as you're coming up to it. And one of the first things you'll notice is that when you get close to a glacier, you drive across this gravelly level plain, probably without very much vegetation on it. And this is the outwash plain. You can't see it down here, but the outwash plain is pretty much the area where all the fine particulate has been washed away by meltwater from the glacier. So it's basically like a giant gravel bed. You may walk along that as you're approaching the glacier. In a lot of situations, there will also be a proglacial lake, which is sometimes bounded by just the topography in the area of the glacier, but can also sometimes be dammed by a moraine. And we'll talk about moraines in a second. Then when you're looking at the glacier itself, obviously it will be beautiful and majestic, and you will be awed. But there are also some large-scale features of the glacier that you'll be able to see as you're approaching it. One of the things is going to be the most obvious, will be the toe of the glacier, the front. You'll also perhaps see sort of channels of debris in the ice that go along with the flow patterns in the ice, and those are moraines of a couple of different kinds. And then, of course, you'll see crevasses along the surface of the glacier. And those are areas where, because of the flow at depth, the surface is in tension, and you're getting cracks opening up in the surface of the ice. And once you get out of your van and you're walking around, you may also see these. So, have you guys all taken Geo 22?
Yep.
So you went on the field trip down to Newport, and you guys used this feature to try to infer the direction of past glaciation and the motion of ice during past glaciation. So these are glacial striations, and there's no scale bar in this picture because I brought you the actual rock that came from right there. So I've got a couple pieces of fresh glacial striations for you guys to pass around. So Who can remind me or remind everyone how glacial striations are formed? If you went on the field trip, you probably have some idea of what creates them. Someone
Come
can
on, you
tell me.
guys.
I know
You're
someone
sitting
knows.
here.
Chris,
No.
you went to Argentina with me, so you're going to be my go-to for...
No, I'm someone who just took Geo 22.
Who just took Geo 22?
How's it formed? Like,
So as the glacier recedes, it kind of pulls off chunks of the rock with it.
So, yes, the
it's
glacier
always
is...
moving forward, not back.
The glacier is pulling off chunks of rock, yes, but it doesn't necessarily have to be receding in this case. So glaciers are always flowing downhill, basically, or away from their peak topography. And we'll talk about that in a few minutes. And as a glacier flows over the rock, it plucks pieces of rock up with it, either from freeze-thaw, from the water getting down into the rock and then freezing and breaking it off, or from just entraining rocks as it goes along. And then it drags those over the rocks. So this would be like the worst nails on chalkboard. But it happens extremely slowly, at glacial speeds, you might say. So those are some of the features that you might see on the ground as you're approaching this glacier. I have an aerial view from Google Maps of this same glacier. And so you can see the proglacial lake in the upper right-hand corner, see the toe of the glacier, and you can see the moraines very nicely. So the one that we saw in the last picture that you could see in the middle of the glacier, that's a medial moraine. So what that means is somewhere back here, two glaciers came together, and there was probably a mountain in the middle. And as the two glaciers came together, they picked up all this debris from the side of the valley as they were traveling, and all that debris merged when the glaciers merge. So usually the medial moraines reflect somewhere upstream two glaciers coming together to make one bigger glacier. And they're formed from lateral moraines. So it's a little hard to see because the rock gets entrained in the ice, and then the ice kind of looks like rock. But along the edges of the glacier, where it's freezing and thawing and scouring along the valley walls, the glacier is picking up rock from the valley walls. So that's why when two glaciers come together, you have all this junk that it picked up off the wall, and they merge together. But you can also see it on the edges of a solo glacier, I guess. So those are lateral moraines. And then, like I said, you can see crevasses all over this glacier. I would guess that Portage Glacier is moving kind of fast because there's a lot of crevassing in the surface. Feel free to interrupt me with any questions you guys have, too. Yeah.
So the lateral moraines
Uh-huh.
differ from medial moraines, the fact that they must be along the side of the
Yeah.
overall
So
flow.
by definition,
By
a lateral
definition, it has
moraine
to
is
be, okay.
along
But a
the
medial
edges.
could be a lateral, or it could be.
So the medial is within a single glacier.
Okay.
So hence the term medial. Like it's within. But it's formed from two lateral moraines that came together and made a medial moraine. So sometimes if you look at a picture of like glaciers from space or something, I should have put one in here, but you'll usually see like glaciers coming down from different mountain valleys and joining together. Where they join together is where you'll get a medial moraine that was two lateral moraines that are now friends, basically. Oh, my computer wants me to shut down Adobe Illustrator. Anyway, okay. So do you guys have any other questions on sort of these large-scale features?
Another one.
Yeah.
So you said crevasses are an indicator of flow rate. So the more crevasses.
That was kind of a back-of-the-envelope thing I was saying. I wouldn't necessarily use that as an actual indicator of flow rate. What they actually do to measure flow rate on glaciers is they'll look at like pieces of debris, like rocks that are sitting on the surface, and you'll just track how far it travels in a day or a month. And they can actually do that via satellite imagery. So you can see a certain feature on a medial moraine from satellite, and you'll just track the progression of that along the glacier with time.
Crevasses are especially produced where a glacier goes over basically a waterfall, right? Because then there's the arc-type tension on the outer part.
Mm-hmm. Yeah, actually, as an undergrad, I once camped on a glacier, and we were right next to an ice fall, is what that's called. It's an ice waterfall, and it's basically a huge arcing mass of crevasses just all cut into it. Very cool. Okay, so those are some fun pictures of those features. They're also a couple of diagrams for the features that you will see. And I can print all this out for you guys, so don't worry if you can't read all the little texts. And also, I borrowed a lot of these diagrams from a textbook that I have, and I think Greg has. So if any of you guys want to do further reading, I can get that textbook for you, or get you chapters, things like that. Anyway, so here are some of the things that I was just talking about. So here's that proglacial lake. Some people call it an ice marginal lake, so that's what it's labeled as here. You get ice blocks coming off the front of the glacier, so calving off the glacier and floating around in the proglacial lake. And here's the outwash plain, very flat. But one thing I didn't mention is if you look at the valley as a whole, it's going to be U-shaped. And you can really, really see this. Chris saw this when we were in Argentina. There was a paleoglacial valley in the side of one of the mountains that we saw in Argentina. And you could see a huge U-shape in the side of this mountain that had been filled in with sediments before it was uplifted as a mountain. So there was a paleoglacial valley in the side of this mountain, which is pretty incredible. But you can see it even as you're driving up. You'll be able to tell that the valley walls are very uniform, very, very U-shaped. Let's see, what else? You'll also, as you're going along the outwash plain, probably see a lot of braided streams traveling along it, through the gravel. And this is usually glacial runoff. So especially during the summer, maybe not as much when you guys are there because it'll be fairly early spring, but as the glacier melts, a lot of water is produced on the surface, percolates down through cracks in the ice and through basically like boreholes produced by the water called moulins. So they're basically just cylindrical holes that go down into the ice just from meltwater getting in there over time. So all that water makes its way to the bed of the glacier and then flows out onto the outwash plain. So in places like a proglacial lake, you'll have a little delta coming out of the glacier into the proglacial lake. And then in other places, you'll just have a tunnel that's opened up in the ice by the pressure of the water flowing under it, and then water flowing out onto the outwash plain. And those also produce some pretty interesting features. So once the glacier is gone, you can kind of see what's going on under it. And you may also see some of these features if the glaciers that you're going to are retreating. So you may see some of these features as you get closer to the glacier itself. And I mentioned earlier that the lake could be dammed by a moraine. Obviously, it's not going to be a medial or a lateral moraine because those are in the ice. So the last type of moraine is a terminal moraine. And that's where, as the glacier sits in one spot and the toe melts, it ablates, debris falls out of the ice that has fallen off the walls or wherever along the path of the ice. And it accumulates in these mounds at the front of the glacier, producing what's called a terminal moraine. And so sometimes, if the glacier retreats further, that will actually serve as a dam for a proglacial lake. But in other cases, you might just see it as a mound of sort of gravel where the glacier used to be. And it'll follow the path of the old toe of the glacier. And you may see a succession of them representing places where the glacier stalled during its retreat. And they've actually seen these on Mars. There were glaciers on Mars, and they've been able to map moraines on Mars as an indicator of when and where there were glaciers flowing on different parts of the planet. So they are large and they're very persistent. Another thing you might see are eskers. And I mentioned that when the meltwater is produced on the glacier and percolates down, forms these streams under the glacier. Well, those go through cycles of high flow and low flow depending on how much meltwater is coming off of the glacier. And when they slow down, as you learned about in Geo 22, when the competence changes of the flow, you drop out rocks. And so you'll actually build up little mounds of rocks that were dropped by these subglacial channels. And so these are called eskers. And they reflect where the largest subglacial channels were before the glacier retreated. And you can see these on Mars too. Let's see. Another thing you might see are drumlins, and these are sort of streamlined mounds that were mounds under the ice. And I'm not 100% sure if the debate has been solved about how exactly these things are formed. It seems sort of natural to me that they're streamlined in the direction of glacial flow, so they're probably scoured by the ice and the rock entrained in it as it goes by. My understanding is that glaciologists still kind of argue, though, about the exact way that they get this shape. The last thing are these kettles, and these are all over Alaska where I grew up. I think my house is actually next to a glacial kettle, but basically, as the glacier retreats, sometimes it'll just drop a piece of ice, and if there's not a proglacial lake, then you just have this big chunk of ice sitting there, and it gets covered in sediments, but eventually it melts, so you end up with this depression where that block of ice used to be, and a lot of times those are little lakes. So if you see a bunch of random little lakes near the toe of a glacier, or where glaciers once were, they may very well be kettles.
That's why cranberries grow so well on Cape Cod, because they're in all their old kettle holes.
They're all in kettles?
Yep.
So nice little bogs?
That's right.
Little low-lying areas? Yeah.
How big typically are the kettles?
I think that they vary in size, but I think a good range would be like around 100 meters, probably less than a kilometer. I don't know, if you have comments on that, Jan, feel free.
Just more history, so Bunker Hill, up around Boston, Drummond.
Oh, there you go. We should have had a field component to this. Could have gone check out a kettle. Drummond. All right. Any other questions on sort of the glacial geology of things that are left behind by glaciers? Or all right, cool. So then the next thing I want to do is talk a little bit about the physics behind glaciers. And I think this is more fun to draw on the board. We'll test my art skills. But I thought it would be boring to just show you diagrams of how the glaciers flow. So in a big picture cross section, here's your hill or your valley.
Yep, I can see.
Can everyone see? So you have an area up here, lots of ice, and then it comes down like this. And this, obviously, your ice is flowing downhill. So there are two major zones of a glacier. Down here, where the ice is mostly melting, it's the ablation zone. Up here, where you can imagine you're up high in the valley, this is be compressed, I guess, but up high in the valley, you're accumulating snow. So this is the accumulation zone. So up here, the glacier has a net gain in snow and ice during the year. Down here, the glacier has a net loss of material throughout the year. So you can imagine that there's some point in the middle where it neither gains nor loses during the year. And this is the equilibrium line. So this is big picture, the various zones of a glacier. So as you're driving up in your little van, not to scale, right, you'll probably drive up to the ablation zone. So here you have meltwater coming out from under the glacier. So you have your outwash plain in this direction. Then you have a lot of melting along here, so this will be mostly pure ice. And then when you get out and you hike up to the glacier, you get higher in altitude. Depending on how high you go, you'll eventually get to this place where it seems kind of slushy and gross on top of the glacier. And as you get even higher, you would get to an area where this all just looks like snow, basically. So you would see a lot of snow on top of the glacier. Down here, you're going to see all ice. And then there's an area in the middle where more complicated things happen. And instead of trying to draw all of the more complicated things, lots of things happening. Don't try to worry about memorizing all of this for when you go look at a glacier. But in this equilibrium area, the zone around the equilibrium line, you can get an idea of all the different processes that are happening inside of a glacier. So above the equilibrium line, when you're in the accumulation zone, the glacier is gaining material throughout a year. And up high, it's snowing. So you have snow, a thick layer of snow that accumulates each year. So this line right here is sort of the layer of, this is last year's snow, this is this year's snow. But when you get close to the equilibrium line, it gets a little warmer. And so some days of the year in this area, it gets above freezing. So you get a little bit of meltwater that forms. And it percolates down into the snow. And so this is called the percolation zone. And you get little ice lenses because the water will percolate down in and then it'll freeze. So you get these cool lenses of ice that form in the snow and fern. And you also get, what are they called? Ice glands, where they don't form lenses, they form these weird branching structures of frozen tubes of water that were trying to make their way down into the ice. So they're called ice glands. And as you keep moving downhill, you get more and more melting happening in your glacier. And you can get so much melting in the wet snow zone that all that water that percolates down maybe hits some ice at the top of last year's snow and starts to accumulate here near the toe, which is called superimposed ice. So you'll get this really clear, fresh ice that kind of pops out near the surface of the glacier at the bottom of this year's layer. And then as you keep on going past the superimposed ice, then you're in the ablation zone. Everything melts, and you'll just see pure ice. So another question that glaciologists have is, if I have snow up here and I have pure ice down here, what's happening in between? And that is where the fern comes in. Can we hit the lights again just so we can see this picture? So up here where these people are standing, like you guys will be standing, it's snow. Then at some depth, that snow has gotten compacted. And that happens through several different processes. So you can imagine the snow falls, it has that nice crystalline shape, but it kind of gets rounded out either by rolling around or by vapor pressure, like relocating the water molecules into more favorable areas. We won't go into that physics. But over time, the grains become more rounded and they can kind of pack together. They can just settle, they can pack together. Then you can also get what's called sintering. So the grains actually kind of grow in together. And as they get buried more and more, the pressure on top of them is building up. So you're actually pressing the grains together. So through this variety of processes, you go from snow, which is loose and very light and fluffy, to fern, which is F-I-R-N, which is more dense than snow, but not quite ice yet. I like to think of it as when you go outside after it's snowed, but it's been a couple of days and it's all kind of gross and thick. That's fern. It's more dense than fresh snow and not quite solid ice yet. And then as you go deeper into the glacier, as it's been buried by more and more years worth of snowfall, then it's gotten pressed together hard enough that it eventually closes off the pores and becomes solid ice. So you go from snow to fern over probably a couple of years worth of burial in a glacier. So when you guys, if you go walking around on the surface of the glacier, you'll mostly be walking on snow. But when you get down to the toe, all that snow has been melted in the ablation zone, and you'll see the ice that was snow from, I don't even know how many years prior, but it'll be old snow that's now ice. Oh, my computer is complaining at me for having Illustrator open. Sorry.
Are you guys, Chris and Nick and Alan, are you guys going to get probably up on the glacier, or is it not sure?
Oh, it's very sure.
That you are getting up on the glacier?
Yeah.
Okay.
Cool. So you'll get a sense for it when you're up there, like the texture of fern. It's like if you make a snowball, where it's definitely compacted, but it's hopefully not solid ice if you're going to throw it at someone, right? But it's not loose snow. It sticks together. And it kind of squeaks when you walk on it. You'll hear it. All right. So for those of you who like data, I don't know, I'm a grad student, so I know there are people who like the data, so the qualitative descriptions. So a glacier is built up, obviously, by having the accumulation that happens in the accumulation zone outweighing the ablation that happens further downhill, right? So overall, they call it the mass balance of the glacier. So accumulation happens through one major process, snowfall. And then ablation can happen through a couple of different processes. Obviously, melting is one of them. Sublimation is another one. So the water can, or the ice can go straight to water vapor. Another one is scouring. So if you're in a particularly windy environment, you can abrade away the surface of the glacier. And for a glacier to grow, you want the snowfall, the mass added to the glacier by snowfall, to outweigh the mass lost by those processes. Of course, in a lot of places on Earth right now, the ablation is winning out and glaciers are shrinking. So Portage Glacier, which we saw at the beginning, you used to be able to see from the highway when I was a kid. And the icebergs in the proglacial lake were right by the highway. Now you have to hike 3 miles to see the toe of the glacier. So ablation is definitely winning out at Portage Glacier right now. But schematically, if you look at a graph of this dotted line being accumulation and this dotted line being ablation through time. So here's time on the x-axis, and this is just positive for accumulation and negative for ablation. In the winter, you're pretty much only gaining mass through snow. But when summer arrives and it gets warmer and warmer, the ablation kicks up and the overall balance of the glacier starts to decrease. So in this schematic, which is an overall growing glacier, you have a net accumulation at the end of the year. If it were a receding glacier, this component would win out and the solid black line would end up below 0. So all this meltwater has to go somewhere, right? So you have a whole another subset of grad students studying glacial hydrology. So you can get proglacial lakes, so water that builds up on the surface of the glacier. You can get moulins, which are schematically here, but basically conduits from the surface down to the base of the glacier that water can flow through. Water can flow into crevasses and then down to the bed of the glacier. And you can either let that water flow out to the toe, or that water can accumulate under the glacier. And you get subglacial lakes, which sometimes open up catastrophically and release a huge flood from the toe of the glacier, called a Jokelhop, I believe is how it's pronounced. And there was actually a massive one in 2011 near where you guys are going. I was Googling this area. They apparently had to close roads. The road that goes to the glacier that you're going to is apparently closed because of this massive Jokelhop glacial outburst flood from the glacier that starts with an M. So that can happen, but doesn't happen very often, so I don't think you need to fear for your safety. But how that water gets from the bed to the toe of the glacier is actually an area full of questions for glaciologists and for people like John Platt, who was here giving a colloquium a couple of weeks ago. There's a lot of research into how the water gets from point A to point B. And so I would like to show you guys a video of how water distributes itself under a glacier and makes its way out to the toe. You see this? Exit here. To the right or to the left? Or up? There it is. Technology doing this to me. Well, maybe I won't get to show it to you because this website's going to complain. But I have a picture of the results. Alright, well, we'll go with the picture and then I'll try to get the video to load later to show you guys. So this is looking at basically a map of the bed of the glacier. So if you were looking down from above and you stripped away all the ice, and this is a numerical model, so obviously it's not in the shape of a glacier bed or anything like that. But what they do is this S represents how much water is at the bed of the glacier. And they basically say, okay, well, if you just put a bunch of water under the glacier, which is blue, what happens to it? And if you just put the water there and then let it flow, sounds like a song from Frozen, then it actually organizes into these channels. And so it sort of self-organizes into channels that form under the ice and then allow that water to pass out under the glacier, which is actually really good if you want a glacier to remain stable, because the forces involved in ice flowing downhill, the strength of the bed is a huge factor in that. And if you guys have taken structure, you know that if you add fluid to a fault, then what happens? Those of you guys who have taken structure, if you've got a fault and you add fluid pressure, what makes it easier to have? Slip, exactly. So if you have a glacier that's sliding along on rock, which is in effect a fault, and you add melt water from the glacier, you actually make it easier for the glacier to slide on the bed, which makes it easier for the ice to flow downhill, which makes your glacier less stable. So when the water organizes into these channels, it actually leaves all this white space in this model where the glacier is bonded to the bed and actually reduces that effect of fluid pressure on the flow of the ice. And then when it comes out at the toe, it actually comes out in these giant channels. So this is a particularly large one. This is probably the size of channel you would expect for one of those outburst floods. But this is the sort of thing that's created by water flowing under the ice. And like I was saying, that has a big effect on the stress at the base of the glacier. So this is just colored based on how hard the bed is pushing back on the ice, trying to flow downhill. And red is pushing back hard, and blue is not pushing back at all. And so you can adjust the amount of pushback by adjusting the water flow along the bottom of the glacier. But that's kind of getting ahead of myself. I wanted to talk a little bit about the forces involved in ice flowing downhill. Because why does a glacier flow? Just ideas. You guys are allowed to speak up. What do you think? Even if you talked about it in Geo 22 some, right? Does the glacier just slide down the hill and snowplow everything out of the way?
A little ice cube, right?
Like an ice cube being pushed? Yes or no? Who says yes? Who says no? Right. So there are some forces involved in what's happening. So if you have, I'm going to draw a little block of ice. So we have this block of ice, and it's sitting on the bed. So here's the rock. This is rock. And it's at some angle. And so you have the ice. It does want to slide downhill. I mean, why wouldn't it, right? So there is a component of it wanting to slide, which is based on the weight of the ice and the slope of the bed. But, like we were just saying, the bed is resisting that. So there's some force from the bed pushing back on the ice sliding. So the main thing that's driving a glacier downhill actually depends not on the slope of the bed, but on the combined effect of the slope of the bed and the slope of the surface. So say the glacier way up high is sloped something like this. If you have a column of ice, then you have pressure at the bottom of that column of ice, rho GH, right? So if the bed is, or if the surface is pretty steeply sloped, then H on this side is bigger than H on this side. You have higher pressure on this side than on this side, and the ice is going to respond to that by flowing. So all of these things work together. The ice wants to slide downhill, the base is pushing back, and it's also being squished and wants to flow like a really viscous fluid downhill because of the pressure change on either side of this block of ice. Then you also have on the edges where the lateral moraines are, you also have some drag from the sides. So all these add together to give you, this is basically speed versus depth in the glacier. So it's a combined effect also, like you talked about in Geo22. So you have the combined effect of all of the different layers of ice trying to flow. But as you get up to top of the glacier, you don't have a lot of pressure driving that flow. So the speed's not actually changing very much near the top of the glacier. The speed's changing most down at the base.
We're talking basically the shape of a pipe. You drill a
Yeah,
pipe,
exactly.
that's the shape it would be
Yeah.
after a few years.
And they've actually done that.
Yep.
So they drill like an ice core and they leave the pipe in there. So on day 1, it's a perfectly straight pipe. And after a year of the ice flowing downhill, the pipe will have this shape. And then this is if you look at the glacier from above. Ice is flowing this way. The edges are sort of pinned. They're being dragged back by the walls of the valley. And the ice in the middle is flowing fastest. So if you did a couple of different pipes in the ice, these ones would be less bent than this one. So the thing that I study the most, which relates to this, is why they have a bunch of different lines here with n equals 1 and n equals 3. And for those of you who haven't taken structure, you won't be as familiar with like a flow law for a creeping material. But it's what I study, so I want to tell you guys a little bit about it, just to give you an idea of the sorts of debates that are happening in the glaciological community. And who knows, if you can bring me some samples of the glacier and we can look for signs of the rheology, maybe we can contribute to this debate. But for those of you who have taken structure and Geo22, you'll have learned about dislocation creep, right? So I've got the image up here, but someone should be able to tell me how dislocation creep works.
You don't know that yet. Okay, so essentially,
You want to draw a picture?
I mean, these two
Okay,
figures are
you're
great,
going to use
but-
this picture.
Sure. So when you break a rock, if you were just to like crack a rock in half, the amount of force that you would need to do that is crazy, and it's not what we see in the real world. We see a much smaller fraction of that. That's because we're not breaking all of the bonds at once. We're just breaking one at a time. So that's essentially what you're seeing here in this figure. One lucky bond gets to break, and everything above it shifts over. And this continues to happen until you see some macro scale deformation.
Yep.
And there's some really cool videos that exist on the internet where you can see these dislocations moving almost like they're alive. They're crazy. You should Google them. I highly recommend it.
It's weird. They march like soldiers in a line. So this little T in this image, these are the dislocations that Chris was just talking about. And all the dots here represent a crystal. So like Chris was saying, if you tried to take this perfect crystal and just shear it, and you tried to break all these bonds at once, it would require this crazy high amount of energy. Crazy high being a technical term. But if you have this defect in the crystal, which is called a dislocation, then when you apply a shear stress to this crystal, the stress on these bonds is higher than the stress on all the rest of the bonds. So these guys will break way before the rest of the crystal bonds will break. And you can just propagate that guy through the crystal, which requires way less energy than trying to break the entire crystal. And you can still achieve the same end result, which is once this guy makes it all the way through, you have changed the shape of the crystal. But you've done it with way less energy. And so in ice, this is a dominant form of deformation inside of a glacier. It's pretty warm, the stresses are high enough, dislocation creep is definitely happening to allow the ice to flow in response to this difference in stress across the faces of this block. But there's this other process that some people think is happening, including myself, some people, being most of the people in this department, called grain boundary sliding. So imagine that all of your ice crystals are really strong. If you needed much more stress or force to make dislocation creep happen, maybe there's another way that the ice as a whole could change its shape without changing the shape of the individual crystals per se. And it's a little bit hard to see, and I apologize, this is low on the slide. But grain boundary sliding basically is what it says. Instead of the ice crystals changing shape as much, they actually slide relative to each other along the grain boundaries. So they can just switch positions instead of changing shape as much. And David Goldsby, who was a professor here, measured the signatures of this happening in ice, and he wrote this beautiful paper discussing why this would be relevant. But people in glaciology don't like it because it depends on the size of the grains. And we can't really say, well, what the exact size of grains is in a glacier or an ice sheet or in an icy moon like Europa or Enceladus. And so the glaciologists prefer to use a very simplified flow law for the ice that pretends that this doesn't happen. And so it's a pretty big debate in the community, and there were some interesting talks at AGU about this. And it's what I study. So if you guys can, find me some good samples and you can look for signs of grain boundary sliding near the base of the glacier without endangering yourselves, then maybe we can write a paper together on this. Anyway, so that's all that I have for you guys. Thanks for your attention.